Good morning, class. This is the lecture for, the video for the September 3rd lecture for energy systems. And today we're going to go over kinetic energy. Okay, kinetic energy is the energy of something in motion. And most of you probably know the formula for it. It's 1/2 mv squared. We'll derive that today. But I want to back off because and start a little bit earlier than that, because the fundamental equation that we'll be using for most of the course is energy is equal to force times distance. That is to say, the energy you impart to something or that you transfer to something is equal to the force you apply to it times the distance over which you do it. For example, if I apply a force to this eraser, pushing it across the blackboard here, I am expending energy, a very small amount of energy, but I'm having to expend energy using my body, ultimately burning the chemicals inside my body to yield that energy in order to make that eraser move across the board. And that energy can be easily calculated if I know the force with which I'm pushing the eraser, and I multiply that times the distance over which I've pushed it. Now, in the case of this eraser being pushed at a constant velocity, okay, its kinetic energy is not changing because kinetic energy goes up with velocity. And so where is that energy going? All right, as I'm doing this, I'm expending energy. It has to go somewhere. Well, where it's going is in heating the blackboard and the eraser due to friction. So, that's the first illustration of a constant theme in this course, which is I want you to always understand how much energy is being expended, how to calculate it, and where it's going. And in this case, because the kinetic energy of the eraser is not changing, it's winding up as ultimately heat. Okay, so getting back to kinetic energy and starting with energy is equal to force times distance. And the variables I'm going to use E here and X. Now, we have to be a little careful with the use of E because we'll be using that for electric field later as well. But for now, using that for energy, we have another equation we know, right? If this is, I'm sorry, this should be F, E. Okay, we have another equation we know, which is that F equals ma. And, that's Newton's second law, of course, where A is acceleration, which is the change of velocity with respect to time. Okay, and now this is a good lecture to start with because it illustrates the level of mathematics that I'm expecting students to have, which is that if I turn this around, right, this becomes dv is equal to F over m t, and so the velocity is the integral of F over m dt, or Ft over m. Okay, so if I push something with a constant force, allowing it to accelerate, its velocity will go up linearly with time. Now, we know what v is. V is dx dt. So if we perform the same integral there, what we will find is that the distance over which it's traveled versus time goes up as 1/2 L over m t squared. Just taking that integral, putting dt over there. And, you know, I'm assuming that everyone has sufficient capability in calculus and such that they can integrate t. All right, and so that's x, and this is v. And so what we want to do here is we want to show that the energy is 1/2 mv squared. So what we want to do is we want to figure out how to replace x with v up there in that equation. And that's pretty straightforward because since we know that v is equal to f over mt, we know that v squared is f over m t squared. And so if we write down that x here is equal to 1/2 f over mt squared, that's equal to 1/2 f over m times t squared, m over f squared v squared. And so energy is equal to force times distance is equal to force times 1/2 f over m over f squared v squared, and you can see that the f's cancel and we're left with 1/2 mv squared. So now you had a physics class at some point, and so you might remember, kinetic energy is 1/2 mv squared. Here what I've done is I've shown that if you push something with a constant force and you allow it to accelerate, that is, it's not like the eraser, it's not like constant velocity, but imagine a little car on wheels that I'm pushing, and so it's accelerating. That energy that you've imparted to do that, F times distance, is equal to 1/2 mv squared, the ultimate, or basically based on the final velocity of the thing you've pushed. So, we've established that kinetic energy is 1/2 mv squared. All right, now that's pretty simple, and we'll be covering other forms of energy, potential energy, and things like that, and you'll see that almost no matter what it is, we can start with this formula here, as we did for kinetic energy. Now, this is going to be a fairly short lecture today because I want it to be relatively focused for our first lecture. And so one of the things I wanted to illustrate with kinetic energy is that you can use this formula to calculate the kinetic energy of a moving system. And the way you do that is that the kinetic energy of a system is equal to the sum of the kinetic energy of the components. Or that's supposed to be sum here. And for example, let's do a flywheel. Now, a flywheel is a somewhat important technological device in the field of energy. It's basically a disc that is spinning. And so, for example, this can be used as an energy storage device. It's often used in a magnetic type system where, for example, if you want to store electrical energy, you can run a current through electromagnets and put magnets on the flywheel so that you spin this thing up very fast. And then if you want to withdraw that energy, you can do it in reverse and basically withdraw the electrical energy by slowing the thing down with the magnetic fields. But you know, those are more details than we care about right now. Right now, I want to know, okay, this thing is spinning, how much energy is contained in it. And the energy is all kinetic, and will we use this principle here? So, how do we do this? Well, okay, so the first thing that you have to do is you know, quantify how fast it's spinning. And the easiest way to do that is to assume it's spinning with a revolution time t, which means that basically it goes around in one cycle in a time t. Okay, so that's the first thing we're going to do. Now, we also have to know things about the mass of the flywheel. And for that, we'll use the, so this is the rotation time. And we'll use rho, the mass density, or the mass per unit volume. So, we have to calculate the total kinetic energy of this thing. Now, the principle you have to use here is that however you divide the system up, you want every component to have the same energy. Or I'm sorry, I said that wrong. Every part of the component that is to say, you look at what's going on here, you look at the system, and how do you identify components to analyze? Well, a component is something where all the constituents of that component have the same kinetic energy, so that you can perform the sum. And for the flywheel, that's pretty easy, because you will note that at a certain cylindrical coordinate r of the system, all the mass elements of that shell have the same kinetic energy. How do I know that? Well, because they're all at the same velocity. Okay? V is a function of r. At a given r, it's the same. So those are my components. My components are these shells at different r. Now, what is the velocities at r? Well, okay. We established that the rotation time was capital T. All right. Velocity is distance over time. What is the distance of one circle? Well, it's the circumference, 2 pi r over t. Now, what is the here I'm gonna sort of jump ahead and realize that I'm going to be doing an integral. So instead of writing the mass of the shell at R, I'm going to write the differential mass of the shell at R, because it will be a differential. Now that's equal to the thickness of this shell times H, the thickness of, or the height of the flywheel. And so now here I always like to do, if necessary, you know, if you have a circle, okay, if that is R and that is R plus dr, now you can see that I'm sort of jumping ahead and going from a summation to an integral here, that the area of that, well, okay, some students will just realize that it's 2 pi r, the circumference, times dr. You can figure that out if you want to, using this as an aside. Okay, the areas of the circle. Okay, pi r plus dr squared, that's the area of the outer circle. And if I subtract the area of the inner circle, okay, and you realize that dr squared is 0, you will come up with 2 pi r dr. So however you need to do it. So the mass of my differential element, the cylindrical shell there, is equal to rho, the mass density, times this area, 2 pi r dr, times h, the height. Density times volume. All right, now basically then I can write down the kinetic energy at a given point r, and so that's equal to 1/2 dm v sub r squared, or equal to 1/2 rho 2 pi r h, and then v, let me erase this, times 2 pi r over t squared. And putting that all together, you get basically 4 rho pi to the third h over t squared times r to the third dr. Okay, so let me, just stop there for a moment. What I've just calculated for you is this shell. Okay, and so what you need to do is you need to imagine, okay, the rest of the flywheel is gone. All I have is this shell. It's like a tin can, an empty tin can spinning there. Okay, if my flywheel simply consisted of an empty tin can spinning, I wouldn't have to do any integral or anything. I would just know, because every mass element of that edge of the can is moving at the same velocity, that the kinetic energy is simply given by this, and then I would have to plug in dr here, whatever it actually was. But what this is saying is that to calculate the kinetic energy of the entire flywheel, I simply sum up all the differential kinetic energy elements, and I perform an integral. So that's pretty easy, because it's basically the integral of that 4 rho pi cubed h over t squared times r to the third dr. Now what is the integral over? Well, it's from 0 to and we'll call this capital R. Zero to capital R. Okay, and so we all know how to do that integral. 4 rho pi to the cubed h over t squared times r to the 4th over 4. That's the integral of r cubed between 0 and r. So that's 4 rho pi cubed h for t squared times r to the 4th, and the 4 cancels out. We could write it in a different form by noting that rho, if the total flywheel had a mass m, rho would be equal to m over the volume of the disk pi r squared h. And so the kinetic energy we could also write as m over pi r squared h times r to the 4th over t squared. So and pi squared, pi cubed, sorry, equal to m pi squared r squared over t squared. I think I've done that right. So we see that we can, that the kinetic energy of this flywheel is proportional to the mass. It's also proportional to r squared, and it's proportional to 1 over t squared, which kind of makes sense because basically the faster you spin it, the more kinetic energy is going to be contained in it. So, I mean, I've just shown a simple example of how to think about energy, particularly kinetic energy, of some system as being the sum of the kinetic energy of different components. Now, one thing you always need to do is check your units. And if you check your units here, you will see that what I've derived goes as mass times velocity squared. Please, in any exam or quiz or homework or anything that I assign, always check the units of your answer. Now, the reason for this lecture, part of the reason, is that I'm going to give you a homework assignment. And that homework assignment, one of the problems anyway, will be taking a sphere spinning with a revolution time t, and I want you to perform the same analysis. I want you to calculate what the kinetic energy contained in that sphere is. So that'll be one of your homework problems this week. The other problem will be more explained in the homework handout, but and we can go over it maybe in class a little bit more tomorrow. But I think this is all we needed to cover in the lecture today. Okay, maybe The other part of the homework, okay, will not be specifically on kinetic energy, but it'll be on this this concept, you know, of that that energy has to come from somewhere and go to somewhere, and I'm going to ask you to evaluate a person on a treadmill at an incline. All right, so this thing is, you know, going that way. So you're on a treadmill on an incline. And how, what I want you to do there is you're going to have to look up on an exercise website what the calories per hour is burned going up a treadmill, and make a conversion. So so I do need to tell you a little bit about that first. And basically, in this situation, you can look up calories per hour. And you need to convert that to watts or joules per second. Now we'll be going over and over units again, but for now, read the text on units and understand how to convert calories per hour to watts. Everyone kind of knows what a watt is, you know, because you're used to thinking about light bulbs and stuff, like a 100-watt light bulb, or these days with LED, that's, well, I mean, usually it says something like 60-watt equivalent in that respect. But anyway, you should know what a joule is. And so all you have to do is look up what that conversion is. You can even look it up online if you need to. And what I want you to be telling me is what the efficiency of the person is. Now, efficiency in regard to, okay, now the person is moving at a constant velocity, so his kinetic energy is not changing, all right? But he is essentially going uphill. I mean, he's not really, but he's on an incline, so as far as he's concerned, he's going uphill at a certain rate. Now, the corollary to this, okay, we need to go over a little bit, that there's energy and there's also power. And power is basically the time derivative of energy. Energy per unit time. For example, joules per second. Now, energy is force times distance. So if we take the derivative of both sides, power is equal to, and if the force is constant, and here the force is constant, he's moving, you know, I mean, basically, you know, forcing himself constantly going up this incline. And I think I used power as W in the text. So this is our most fundamental equation. Energy is force times distance. This is the corollary to that, which is power is force times velocity when force is constant. You have to realize that, taking the derivative. And so the problem is one of figuring out how much power, how much useful power he is delivering in lifting himself against gravity. Now, the force of gravity most engineering students know, but and we just have to assume here, is the mass times the gravitational constant acceleration, and this is 9.8 meters per second squared. So that means the power of lifting is equal to mg v, where v is in the vertical direction. So when you do the problem, you have to come up with v vertical. So there's a fair bit to this assignment, and what I'm going to do is I'm going to give you at least a week. I'll decide what to do here to do both problems. Okay, that's it for today. So we'll meet in the chat session tomorrow.